Hello students, we will be starting with the formulations of FEM from today's class. And in today's class, the first element which we are going to take, which is going to illustrate how FEM formulation is supposed to be done, is going to be a simple bar element. Bar is a simplest case of strength of materials which you have studied. It is a simple element which is deformed, which undergoes axial deformation. There is no twisting, there is no bending. It supports only tensile or compressive loads. Both these loads are obviously acting towards the length of the bar, and all the assumptions which were made when we were studying this bar element under your BTech classes are going to be applicable in the derivation of the bar element in finite element method also. Apart from this, the current lecture, which is devoted for bar element, because it happens to be the first element for which we are developing the equations. The current session of lecture is also going to illustrate various techniques which are available for obtaining the equations, stiffness equations in local domain. We are going to develop the equations. Excuse me. We are going to develop the equations using the normal stiffness method or the direct method, because this happens to be the simplest one, and it gives a very basic exposure to the persons who are learning FEM for the first time. Apart from this, we are going to develop the equation using the potential energy method, which is also known as the variational approach. This method is the most versatile method and is going to be used to develop the equation when you have plenty of nodes, plenty of degrees of freedom for which the element is being taken. And this method is going to be supported by this method is going to be used when you are developing the equations for cases such as plane strain, plane stress, axisymmetric deformations, three-dimensional and more beams or shells. This is the method which is of immense practical use. Then we are going to develop the equation of the bar element using the Galerkin approach. Galerkin approach is obviously also very versatile, but is used when you have the differential equation at your disposal. And Galerkin approach has already been illustrated in the previous classes, but still for the sake of continuity and for the sake of completeness, the bar element is going to be developed using Galerkin method also. Apart from this, the lecture series is going to give you some exposure of local stiffness matrix, global stiffness matrix, and how the process of assembly is being done. We are also going to have a look upon the boundary conditions, types of boundary conditions, how they are going to be imposed on the global stiffness matrix, and how we are finally going to obtain the solution to the equation which have been derived. So we start with the first method, that happens to be finding the stiffness matrix using the displacement method. So under the current session, we are going to define the stiffness matrix. We are going to derive the stiffness matrix of a spring element, which is the bar element. We are going to demonstrate how to assemble a stiffness matrix into a global stiffness matrix. We are going to illustrate the concept of direct stiffness method to obtain the global stiffness matrix and solve the spring assemblage problem. We are going to deal with the boundary conditions. We are going to show how the potential energy approach can be used to derive both the stiffness matrix of a spring and solve the spring assemblage problem. Now coming to the stiffness matrix itself, the stiffness matrix is a relationship between the nodal forces and nodal displacements. And when we are talking about nodal forces and nodal displacements, we tend to generalize this particular definition in the sense that though nodal forces and nodal displacements are terms which are normally being used in strength of materials, but the stiffness matrix is going to be applicable for non-strength cases also, such as those exist when we are dealing with fluids or when we are dealing with heat cases. The relationship between heat sources and the temperature is again going to be termed as a stiffness matrix, though the actual stiffness is not really present in heat and fluid cases. Now, this relationship is expressed mathematically as F is equal to K into T, where F happens to be a column vector. Note how a column vector has been written. It is written within curly brackets. F represents a column vector. D represents the nodal displacements, which again happens to be a column vector. Therefore, the same type of brackets have been used. But the relationship between F and D is going to be given by a matrix known as the stiffness matrix, which is going to be a square matrix. Therefore, we are using square symbols to represent the stiffness. Apart from this, the size of the stiffness matrix is going to be governed by the size of the nodal displacement matrix, because obviously the mathematical rules which are required for manipulating matrices is going to be followed. So if we have an element which has two nodes, and let's also assume that we have only 1 degree of freedom for every node, that means that the element itself is going to have 2 degrees of freedom. Therefore, the size of the B matrix, that is nodal displacement matrix, is going to be 2, that is 2 row and a single column. Similarly, the force matrix is also going to be of size 2 rows and single column. Therefore, the size of the K matrix which is involved is going to be 2 by 2. It is going to be a square matrix of size 2 by 2. Now, the other thing which is going to be developed in future is that this particular matrix is going to be a symmetrical matrix. This is one thing that you are going to see in future. K matrix is going to be a symmetrical matrix. Apart from this, it is also going to be seen that the K matrix is going to be a matrix whose inverse cannot be found, because it is going to be a singular matrix. Matrix is a singular matrix when its determinant is 0. So it really appears odd why the K matrix is going to be a singular matrix, but singular matrix represents a rigid body motion. Rigid body motion, I mean, if you throw a ball if you throw a cricket ball, so the ball obviously is going to move from one position to another position. That is, it is just moving in space. But while it is moving in space, it is also going to rotate about its axis. So the body is not deforming, but it is actually moving in a space itself. So for these type of motions, uh, the equation which is going to be used is a rigid body motion. But for the cases of for a body to deform, it really is necessary that the body should be constrained at some particular point. So unless the body is constrained, the body is going to be the body is going to behave as a rigid body, which is going to be indicated by a singular matrix. So in finite element method, the representation of the spring matrix, spring element, is on display. Uh, it has two nodes located at its two ends. The left node is node number one, the node at the right happens to be node number two, and the x-axis is always going to be from node number one to node number two. It could have been the case that the right node is node number one and the left node happens to be node number two, in which case the convention is going to be that the x-axis is going to be from right towards left. So the positive x-axis is always from node number one to node number two, but it is not necessary if the left node is node number one. The right node could also have been termed as node number one. Apart from this, both the nodes have deformation indicated by u1x, u2x, and there happens to be a force acting at both the locations given by f1x and f2x. The meaning of terms such as f1, f2, u1, and u2 is obviously known, but the force has a subscript x also. In fact, there should have been a subscript for deformation also. X has intentionally been written over here because there are going to be cases when we are going to see that forces is acting at a node along more than one directions. I mean, there might be a force acting along the x-axis, there might be a force acting along the y-axis also, and similarly along z-axis also. So we have intentionally written f1x. And this happens to be the relationship between deformations and forces. There are the size of the deformation and the force matrix happen to be 2 row and 1 column. And the K matrix, which is appearing in between, happens to be the Stokes matrix of size 2 by 2. Please observe that the K matrix has 4 terms given by K11, K12, K22, K21, and K22, where obviously the terms such as 1 and 2 have been written down in a local format and represents the row and the column number. And since this particular matrix is going to be a symmetrical matrix, excuse me, this particular matrix is going to be a symmetrical matrix, the numerical value of K12 is going to be equal to K21. Apart from this, just for the sake of discussion, if the value of d2x is 0, if the value of d2x is 0, it means that the first equation reduces to f1x is equal to k11 multiplied by d1x. So this means that since the force and the deformation, that is f1x and d1x, both these two things are supposed to be acting along the same direction. If they are acting along positive x, so both of them are going to act along positive x. If one of the things happens to act along negative x, so the other is also going to act towards negative x. So both of them are either going to be along positive x, or both of them are going to be along negative x. So this means that the k11 which is involved in the relationship is going to have a positive number. It is not going to have a negative number. Similarly, the same discussion can be applied to k22 also, since the direction of f2 and t2 is going to be same. The numerical value of k22 is also going to be a positive number. The other two values, that is k12 and k21, might turn out to be positive, or both of them might turn out to be negative. That really depends upon the case which we are talking about. Now on the display we have two figures. The upper one represents a spring element when we are talking about finite element. The lower one deals with the same spring element, that is element under tension, but it uses the terminology which is used in strength of materials. So in both the cases, we have two nodes represented by node 1, node 2. We have the same stiffness represented by K, and the deformation at both the nodes happen to be along the same direction. But if you observe the two diagrams for the forces, you will notice that at node number 2, the force is acting towards the right, and the tension T is also acting towards the right. But when you see the forces acting at node number 1, in the FEM approach, the force is acting towards the right at node number 1. But in the strength of materials, because we have a tension over here, the tension T is acting towards the left, because we always assume that the spring material is going to be under equilibrium. Therefore, if the tension is acting towards the right at node number 2, the tension is going to act towards the left at node number 1. Apart from this, all the directions happen to be same. Only the tension and the forces at node number 1, they are acting in the opposite directions. Now what we are going to do is that if we are going to derive the stiffness equations, we are going to start from the theory which we have already studied under the strength of material case. That is, we are going to derive the equations using figure number 2, and then using the sign convention, the equation derived are going to be converted to FEM. So this is how the derivation is done. The deformation of the spring is given by delta, which obviously is equal to U2 minus U1. And when this deformation is multiplied by the stiffness of the spring, we get the value of tension T. This is how the derivation is being done under your from the strength of material from the strength of material approach. So we have equation number 1, T is equal to K multiplied by U2 minus U1. And now we come to the spring element. And we are going to use this sign convention. Now since at node number 1, the forces acting in the FEM element is opposite to the direction of tension. So F1x is equal to minus T. That is one relation which we have at node number 1. The other relationship between force and tension is at node number 2. That is F2x is equal to T. And then we substitute the value of tension in these two equations. And adjust these two equations in a matrix form, which gives us equation number 2, which really is the stiffness matrix involved. So we see that the stiffness matrix which has been derived, it is a square matrix, of course. Apart from this, it also happens to be a symmetrical matrix because the term which is present in first row, second column is equal to the term which is present in second row, first column. So this is a symmetrical matrix. Apart from this, if you just find out the determinant of the stiffness matrix, it is coming out to be 0. So this particular matrix happens to be a singular matrix. It obviously means that if the value of forces acting at the 2 points is given, and since the K matrix involved happens to be singular, we cannot find the value of U1 and U2 using this particular matrix. So for finding the value of deformations, that is U1 and U2, we are going to impose some boundary conditions. We are going to impose some constraints on the deformation before we actually solve this particular set of equations. Here, K is called the local stiffness matrix for the element. It has some properties which we have already been discussing. It is a symmetrical matrix. It is a square matrix, of course. It is singular. That is, the determinant of K is equal to 0. So the K matrix cannot be inverted. The singularity of K needs some explanation. A singular matrix K represents a rigid body motion. As we have seen earlier, the motion of a ball when it is thrown from one point to another represents a rigid body motion. So a rigid body motion might be undergoing some translation also. It might be undergoing some deflation also. And it is just possible that both these motions are present simultaneously. It can be solved only when proper boundary conditions are imposed on it. In the following slide, we are going to develop the concept of global matrix, boundary conditions, and the solution process with the help of an example. So the example which we are going to take is a very elementary one. Since it is elementary, it has to illustrate the feature of assembly also. So the simplest example which we can take happens to be an example containing only 2 elements, element number 1 and element number 2. And correspondingly, there are 3 nodes. One at the left, which really is a constraint, which is a constraint node. There is a node at the center, that is node number 3, and a node present at the right, that is node number 2. Then there is some forces which are acting at node number 2 and node number 3. And the x-axis is from left to right. This happens to be the global x-axis. And apart from this, the element number 1 has a stiffness represented by K1. Element number 2 has a stiffness represented by K2. So we have already derived the elemental equation for a spring. That is the equation depicted in yellow. We are simply going to apply this particular formula for element number 1 and element number 2. That is one by one to get the respective stiffness equation. So for element number 1, we get equation number 1. For element number 2, we get equation number 2. And in these 2 equations, please note that the forces and the displacements have been written in terms of the nodal numbering. So the forces in element number 1 happens to be F1x and F3x because element number 1 has two nodes, 1 and 3. And similarly, it has two deformations given by U1 and U2 because it again has two nodes, 1 and 3. And there is also a superscript 1 which has been written over the forces and the displacements, which represents that this particular term is being used for element number 1. Similar thing can be observed for element number 2 also. So the stiffness matrix of both the elements has been developed in a local sense. By local sense, I mean that if there is a domain which has been divided into a number of elements, you take the first element and develop its equations irrespective of the other elements which are present. You always develop the equations of the elements one by one. Now, to achieve this solution, we have to satisfy some continuity or the compatibility requirements. And since node number 3 is actually common between both the elements, it really means that the deformation at node number 3 for element number 1 and element number 2 is basically going to be the same value, which we have represented simply by U3 in this case. So this actually is a constraint equation between the two elements. And with the help of this constraint equation, we are going to assemble the stiffness matrix of the two elements. The assembly process requires the force equilibrium, for which we are going to draw the free body diagrams in the next slide. So this is the problem which has been depicted once again. For drawing the force free body diagram, we always tend to isolate the bodies. We always tend to isolate the bodies or the elements, and then we depict all the forces which are acting on the section which has been isolated. So we have isolated element number 1 at the moment. It has two nodes represented by N1 and N3 on the left and on the right. Similarly, we have isolated element number 2 also. It has node 3 and node 2 at the left and the right end. And then coming to the forces acting on this element, the solution which we are doing follows the FEM approach. In fact, we always are going to follow the FEM approach, under which the forces are always going to be towards the positive x-axis. And since in this particular case, the x-axis is from left to right, for both the elements on display, the forces are from left towards the right. So for element number 1, we have the forces on display given by F1x and F3x. Similarly, for element number 2, we have the forces given by F3x and F2x. Then we isolate the node also, that is node 1. Please note that the direction of force acting at N1 is opposite to the direction of force acting at N1 for element number 1, because ultimately when these two nodes overlap each other, the two forces are going to cancel out each other. Similarly, we have forces acting on N3 and we have forces acting on N2. And then as a last step, we are simply going to carry out the force balance at the three nodes which are indicated in purple. So we have F1 acting towards the right at node number 1, F3 acting towards the right at node number 3, and F2 acting towards the right at node number 3. And then we will do the force balance at these three locations, which is going to give us three equations. This is equation number 1 for node number 1, equation number 2 for node number 2, and equation number 3 for node number 3. And in the next step, we simply are going to substitute the value of forces, that is small f 1x for the first element, small f 2x for the second element, and similarly the two forces existing in the right hand side of the third equations. We are going to substitute the value of forces from the elemental equations into these three equations to get these three equations, which when adjusted in matrix form gives us a 3 by 3 global stiffness matrix. Now this matrix which you get is not a local matrix, it is a global matrix because it has contributions from both the elements. The size of the global stiffness matrix obviously is going to be 3 by 3 because there happen to be three unknowns, that is deformation, and three forces. Please note that in this particular case, the stiffness matrix is going to involve a known value of force for which the unknown value of displacement is going to be solved. This is the common approach of FEM. There, in fact, happens to be another approach also, in which we know the value of displacement for which we are going to calculate the value of forces. But that particular approach we are not going to really do in this particular session. So we get a stiffness matrix. It is a square matrix. The global stiffness matrix happens to be symmetrical also, as you can see. And if you just find its determinant, it is going to come out to be 0. Therefore, it represents a rigid